Hello everyone, welcome to the video 7.2. In this video, we are going to talk about the type of mechanism for nucleophilic substitutions of haloalkanes. So there's two different types of mechanism. The first one is SN1 mechanism, which also known as the unimolecular nucleophilic substitutions. So the S stands for substitutions, N stands for nucleophilic, and then 1 refers to this unimolecular. And the second type of mechanism is SN2, so bimolecular nucleophilic substitutions. Again, S stands for substitutions, N stands for nucleophilic, and then bimolecular refers to the number 2 here. So in the latest slide, we're going to talk about what it means by unimolecular 1 and bimolecular 2. Alright, so first of all, let's look at the SN1 mechanism. We want to look at the characteristic of this SN1 mechanism. So first of all, the name is unimolecular nucleophilic substitutions. So for this SN1 mechanism, it is the first order reactions, as the reactions rate depends only on the concentrations of haloalkane Rx. Okay, the reasons why it only depends on the concentrations of Rx is due to this rate determining steps, which is the first steps. Okay, we will explain this one in detail in a while. And since this SN1 mechanism is a first order reaction, so we are able to write out the rate law. Okay, so rate equals to K times with the concentrations of haloalkane raised to power 1, therefore first order. So what it means by rate determining steps? So the characteristics of this SN1 is that it involves a two-step mechanism. So in the first steps, it involves the heterolytic cleavage of the haloalkanes, and there is a formations of carbocation. So this formations of carbocation is a slow reactions, and we call this first step is our rate determining steps. Therefore, the first order of reactions depends only on this rate determining steps. So only haloalkanes is involved in the first steps. And then they will carry on for the second steps. Nucleophile will attack at this carbocation. Okay, and then the second step is the fast reactions. And since only haloalkane involved in these first steps, the rate determining steps, that's why the name is called unimolecular. So the latter ones refer that only one species is involved in this rate determining steps. And another important characteristic of this SN1 mechanism is that carbocation is involved as the intermediate, so a species between a reactants and the products. For order of reactivities, the least reactive towards SN1 mechanisms go for the methyl halides, followed by primary haloalkane, secondary haloalkane, and the most reactive towards SN1 mechanisms will be the tertiary haloalkane. Okay, so increasing rate of an SN1 reactions. And the factors that determines the reactivity of haloalkanes towards SN1 mechanism is the stability of carbocation intermediates. As we know that for this tertiary haloalkane, it will generate the most stable carbocation, the tertiary carbocation. And then for the methyl halides, it will form the least stable carbocation, which is the methyl carbocation. So stability, tertiary carbocation is the most stable, followed by secondary. Primary and methyl is not so favorable. And in terms of carbocation, you need to be aware that whenever you form this carbocation intermediate, rearrangement is possible until a most stable carbocation is obtained. So the priority go for 1,2 hydride sheaf if there is any hydrogens present at the neighbor carbon, or if there's no hydrogens present, then we will go for 1,2 methanide sheaf. So for example, tertiary haloalkane favors SN1 mechanism because the heterolytic cleavage of these tertiary haloalkanes will form a very stable tertiary carbocation. And it is stabilized by more alkyl groups, which is your electron-donating groups. Hence, it is more stable and more reactive towards SN1 mechanism. Next, let's try the first example questions. So outline the mechanisms for the reactions below. Here you have an haloalkane, and this haloalkane is a tertiary haloalkane as the bromine attached to a tertiary carbon. So this carbon having 3 carbon enable. Okay, so when you react with water, this is hydrolysis. We substitute the bromine with the OH, okay, to give an alcohol, a tertiary alcohol. So you may want to write down the delta positive on this electrophilic carbon and delta negative on this bromine. So this haloalkane is our electrophile, and then water being the nucleophile. And then bromine is being substituted by the OH to create its tertiary alcohol. And don't forget that there's a side product, HBr. So the hydrogens from the H2O and the bromine from the haloalkane. As we know that tertiary haloalkanes will generate the most stable carbocation. So for these reactions, it favors SN1 mechanism. So in our SN1 mechanism, there's two steps. The first steps, the formations of carbocation, which is the rate determining steps, followed by step 2, nucleophile will attack the carbocation. So in the first step, showing your tertiary haloalkanes, remember to write out your delta positive carbon, which is the electrophilic carbon. So reactions will happen at this carbon. All right, and then we have a delta negative bromine. So for these haloalkanes, it will start off with heterolytic cleavage for the CBr bond. So the heterolytic cleavage means that from the center of the bonding, both of the electrons will go with the more electronegative bromine atoms. And now we are generating a tertiary carbocation, which is the most stable. So this is your first step, which is your rate determining steps. Remember to write out rate determining step for this first steps. And after this heterolytic cleavage, we also producing this Br minus as a leaving group. So in the second step, nucleophile will attack the carbocation. So in this example, H2O is the nucleophile, so showing the lone pair. So the arrows are coming out from either one of your lone pair and then attacking the center carbon bearing the positive charge. And then now you have a protonated alcohol. But in our predictions, we need a neutral alcohol, okay, a neutral products. So the next step is to remove one of the hydrogens. So this process is what we call as the deprotonations. So taking the leaving group just now, Br minus, so it was going to get one of the hydrogens. So when you make one bond, you are going to break this OH bonds from the middle of the bonds and goes towards the positively charged oxygens. So now you have the products, the tertiary alcohol and the side product HBr. For the second example, given in the questions, you have the name of the structures 2-bromo-3-methyl-butanes react with a base. So for these questions will involve rearrangement, but remember that the questions will not tell you whether a reactions will involve rearrangement or not. So you have to go through the mechanism. So when you see a carbocation, you need to stop and think, is there any rearrangement required? So this is the structures for 2-bromo, 3-methyl-butane. And then with a base, you can suggest either you want NaOH, KOH, or OH minus. So this is a substitutions reaction. So OH minus will substitute the bromines to produce this alcohol and the leaving group Br minus. But you will realize that this substitution is not exactly at the positions where the bromine initially attached to. So we have to go through the mechanisms to predict the product form. Right, so for this haloalkane, as bromine is attached to a secondary carbon, therefore this is a secondary haloalkane. So secondary haloalkanes will also produce a quite stable secondary carbocation, therefore it's still favorable for this SN1 mechanism. So we start off using this haloalkane. So remember to write out the delta positive carbon and delta negative Br. So first of all, we need to break out this CBr bond using heterolytic cleavage. So from the center of the bonding, both of the electrons go towards the more electronegative bromine. So this first step is our rate determining steps, as it will form this secondary carbocation. Remember that when you form carbocation, always write down the class of carbocation. So from here, you will stop and think, is there any rearrangement possible? If yes, then we will proceed. So now you can see that focus on this secondary carbocation where you have the positive charge, and the neighbor carbon next to it, it has one hydrogen and one CH3 a methyl group. So that means we have the possibility to form a more stable carbocation. So the priority go for the 1,2 hydride shift if you have the hydrogens at your neighbor carbon. So it will proceed with 1,2 hydride shift. So now the hydrogens, so imagine the hydrogens at the neighbor carbon here now change the positions to this second carbon here. So hydrogens change the positions with the positive charge, and now you are getting a more stable tertiary carbocation. So this process is 1,2 hydride shift. So once you got the most stable carbocation after rearrangements, then we are proceed with the second step in the mechanisms, which the nucleophile will attack the carbocation. So for this nucleophile OH minus, remember that the negative charge fall on the oxygens, and we are going to create this CO bond. So the arrows will start from this oxygen. So taking your nucleophile, and then it's going to attack the center carbon barrier with a positive charge. And now you are getting your final product. So this final product is what we're predicting earlier. But if you couldn't predict these products initially, hopefully with the mechanisms you are able to identify the correct final products. So this is the example with SN1 mechanism which involve rearrangement. So that is the first part of the video talking about the SN1 mechanisms, and I'm going to see you in the next video.